Okay, so now we've been doing these, and they seem fairly straightforward, maybe. So now let's remember something that'll make them complicated, because this is calculus-based physics, and it's also hard. So don't you forget about, what am I going to say? K. Bum, 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 bum. Rotation. Oh, yes. All these things have been masses, and they've just been not rotating at all. So we haven't wasted any energy on rotational motion, have we? They kind of did rotate when they came down, didn't they? Oh, no. Let's not worry about it. But now we're going to let it roll, okay? So we're going to have a ramp. It's always a ramp. Like this, like that. It's some angle theta. Ramp comes down. And we're going to have a disk roll. Would you get the same answer if you did to C? I think you mean A to C. Then yes, you'd get the same answer. Okay, so here's our disk. So it's like a solid, like that. There we go. And it's got mass m and radius r. And we start out at a height h, like that. You'll notice I'm being a little vague about where I draw the line on the object. And it does matter. Technically, you'd go with the center of mass, this height here. So it'd be, I'm drawing it kind of to the bottom. It's actually another radius up. But when you're down here, it's also another radius up. So it kind of cancels out. Right? So if you watch your geometry carefully, as long as you're talking about the same point, it won't matter. Okay? If I raise this up to the center of mass here, I would say, well, I don't quite get to 0. I get to r. So that's why I'm not worrying about it. Okay? So it's kind of a detail for your problems, won't make a difference. Okay? So the height that we're dealing with is right there. Okay? And the question is simply, how fast is it going to go here? How fast is it going to go there? Okay, so now it's not quite so easy, is it? Because before you'd have said, oh, well, mgh equals 1f mv squared. This is now the third time we've done that. But you can't do that now, because you're going to have two kinds of kinetic energy. It's going to be translating, and it's going to be rolling. Right? So we've got to deal with both. So for that, you probably should go to your energy formulas here. So let's use this one. Let's do before and after. Okay, ui plus ki equals uf plus kf. Initial energy equals final energy for an isolated system. What is the initial potential energy? mgh. Okay, we're going to go faster now, right? If we said, oh, I forgot to say, here u is 0. Right? On the ground, there is no, we'll define that as 0. Okay. So mgh is the initial, what's the initial kinetic? What's the initial kinetic? 0. Wow, you guys are, we're in the 9th week. Y'all are warming up to me here. Okay, and now that's equal to, what's the final potential? What's the final potential? Okay, 0, right? So initial kinetic was 0 because it wasn't moving. Final potential is 0 because it's reached the bottom where I said was 0. So now the hard part. What is the final kinetic? What's the final no, you're too smart. The final kinetic is that it's rolling. So we say, okay, 1f mv squared. That's the translational part. And now you have a panic. What's the rotational part? Oh my God, I don't know. Oh wait, I have a formula for that. Plus 1/2 I omega squared. And you turn it in. And you don't get all the credit, right? Because there's more to it than that. We want to see if we can get it farther down than that. Right? So we say, okay, that's all right. Let's start filling in here. Equals 1/2 mv squared. Plus, we want to get everything in terms of m and v. Because we want to think about how it moves down the ramp. And the question was how fast. And by that we mean v translational, not rotational. So we want to get the rotational part in terms of the translational part. Right? So we want to say 1/2 is the same. I for a disk is 1/2 mr squared. You got to remember that or look it up. Mr squared. Right? And now we need the relationship between omega and v. It's got to remember back to our rolling motion. If it's rolling without slipping, that means that the translational velocity is equal to the edge tangential velocity, and that was that whole v equals omega r thing. Remember, s equals theta r, take a derivative, v equals omega r. So omega is v over r. Right? So we put a V over R and square it like that. Right? Interesting. So I would say get rid of the masses. Wow, it doesn't depend on mass. That's weird. Totally independent of mass. Then I'd probably say GH equals 1/2 V squared. Now we've got to do something with this big mess here. Right, squared. That's a fourth. I'll do that part. Okay. Now when we square this, what's going to happen? We have R squared out here because of the moment. We have R squared in here because of omega, and they're going to cancel once we square that. So this is just V squared. That's all that's left. What? Look at that. So these two terms turned out to be the same variable. They're both in terms of V squared, just so we have 1/4 and 1/2. So we have 3/4 V squared. Look at that. So it's going to go down to 3/4 V squared. So now we solved the question was, what is V? Right, V trans. I mean, that's what this is. This is all V translational. It's like how fast it's translating, and it's translational kinetic energy. So we solve it, 4/3 G, take the square root, and we get that the V that we're looking for is the square root of 4/3 GH. All right. Square root of 4/3 GH. Interesting. Why is that interesting? You may argue that it isn't. I don't know. But here is going to be why. Oh my God. I have a big mess. Ready? This is like the dinner thing. You ready? That's not bad. Okay. You should have seen that. That was amazing. Okay. So here's the demo. You ready? So I have a solid cylinder right here. We're going to roll it down. Look at that. It rolled down. No. Okay. So here's the interesting part. Look at this. What does this imply? Does it depend on the mass? No. That would imply that two cylinders like this will go down at the same speed. You have this little cylinder here, this big cylinder here. This one's actually heavier because it's metal. Anyway, clearly not the same radius, not the same mass. And this would say that they're going to end up at the same speed, which basically means they'll go down together, because at any point they should be going the same speed. If I pull this out just right. Look at that. They stayed together. And we can even do... and then we can further learn from this, though. So we just solved that. We were blown away that those stayed together. I know you're still gathering yourself. Just it's okay. Captain Butler. All right. And so what we're going to do now is have another mass go down. Okay. You know what that is? I'm shocked. Okay. Now let's do like a little, like a, what is this called? A thin shell. If we redo this whole calculation with a thin shell, what's the only place it's going to be different? MGH, 0, 0, 1 FME squared, I. The only difference is I, right? So I'm just going to rewrite that one equation. Here we go. MGH equals, I've taken the zeros out, 1/2 mv squared. There's a thin cylindrical shell. I think that's obvious from the drawing, but I will. A thin cylindrical shell. Equals 1/2 mv squared plus 1/2 I. What is I for the thin shell? You can work on your intuition. All the mass is at radius r, so it's just mr squared. It's not 1/2 mr squared. Right? The disk has a lot of the mass close to the axis, so that lowers the moment. This is the biggest moment you can get, is to have it all at the edge, 1/2 mr squared. And then omega, it's still rolling without slipping. So this is still v over r squared. Right? So all it does is it changes the little fraction here. Okay? That little half is missing, which means this basically turns into 1/2 v squared plus 1/2 v squared equals v squared. So this one will go down at v equals the square root of GH. Right? Instead of 4/3 the square root of GH. Right? So this will imply a couple things. It'll say that any two cylindrical shells should go down at the same speed, just like any two solid cylinders went down at the same speed. So here's two shells. Let's see, do they go the same speed? Yes, they do. I feel like I'm at the fair. Oh, loser. All right, who's next? All right. In many ways, it's like being at the fair. Like the carnival barker. Wow, I've got to write an essay. This is like, I am a carnival barker. Okay. So same speed. Okay, so now what we could also learn from this is look and say, wait a minute, this one should go down faster than this one. Who's got 3 tickets? Right? That's 1.33, this is 1. So that would say that the solid cylinder will always beat the hollow cylinder. Oh, but let's make it more amazing. Let's do the big, no wait, which one's going to go faster? The solid's going to go faster. Let's get the little solid cylinder and the big. There we go. The little one will go faster because, oh, I need more training. The little one will go faster because its equation is different, right? Because it's got the 4/3, and the other one just has a 1, right? Look at that. The little one, the solid one, went faster. Unbelievable. Oh, I have one of these, and we don't really have time to do anything else. Oh, we have 5 minutes. God, nothing I hate more than 5 minutes. So if we derived it for the sphere, what would we put? Does anybody remember the moment of a sphere? What number goes here? 5. It's got a 5 in it, yeah. 5 seconds? No, almost, yeah. 2/5. There you go. I'll raise your grade to a C-. Very good. Just kidding. So there'd be a 2/5 here. All right, and what would that do? That would turn this into like 1/2 plus 1/5, which would make it 7/10, which would put a 10/7 here. Puts a weird note. What is 10/7? Is 10/7 bigger than 4/3 or smaller than 4/3? Oh, it's very close. All right, 10/7 is slightly bigger than 4/3. So the ball should beat the big heavy metal aluminum cylinder because 10/7 is bigger than 4/3. Yeah, it is. Yeah, it is. Oh, the ball wins. What do you know? We can't lose. Okay? So that's an example of a more complicated problem. All we did was bring in rotational kinetic energy. It is more complicated, though. Okay, my energy diagrams I'll combine with next Thursday. Let's just do that. I don't want to dive into molecular structure right now. Are we okay with that? We don't want to get in. Oh.